So today I'm going to talk about the applications of mostly fixed mode diffusion Monte Carlo from material science perspective. So here is the short outline. You'll basically talk about the applications that are towards benchmarking with QMC. So I will talk about some of the PhD work that I did for the high throughput formation energies, and I'll talk about the rest of the things that I'll talk about during my postdoc, and the transition metal oxides, and I'll use the cobalt monoxide as an example. And we will talk about the nanoscale materials, understanding the behaviors of the nanoscale material diffusion Monte Carlo, and there will be two applications of different problems: the excited space of manganese insulators and lattice modulation in epitaxial lanthanum cobalt. And I'll briefly talk about the algorithm improvements in the QMC PEG code, which enable some of these calculations, which are actually quite large. So first is the high throughput diffusion Monte Carlo calculations. So the main motivation for doing this research is that when we look at the DFT calculations for the formation energies, or when we just basically compare the different polymorphs of a compound, which is in this case manganese dioxide, we are seeing that there is this kind of shift between the calculated and experimental formation energies, and not all the DFT functionals are really successful in getting the right energetic ordering between the manganese dioxide compounds in here. So what we can actually do in here to improve the results of our calculation. So what we did in this paper was to show that we can actually choose different materials from the CODATA database and calculate the formation and properties of these materials using diffusion Monte Carlo. And we aim to do that by using a fixed scheme or recipe of calculations, so that these calculations can be done with minimal user interaction. So looking at the compounds that we have in here, let me walk through you this figure in here. So we have the quantum espresso calculations with a non-conserving pseudopotential, which are in orange, and the QMC calculations are shown in green, and the last PAWE calculations are shown in black. So you can see that for almost all the compounds except the three in here, which are also indicated in the periodic table with the red color in here, we are seeing that the diffusion Monte Carlo is able to perform better than all the methods that we investigated in here. So we have only looked at two transition metal oxide compounds, basically, which are the titanium dioxide and zinc oxide, and those are actually the closed shell compounds. So we were actually playing it safe in terms of performing the wave function optimization without limited user interaction. So we can see that we can compare the performance of our calculations to the well-known materials databases. So in that sense, we already know the materials project database, and also the open quantum materials database is a good example. So when we see that actually there are a very large number of compounds in here, more than 103,000 compounds, but we are seeing the mean absolute errors of nearly 0.1 to 0.13, that we also need to consider that these errors are minimized as much as possible using the flux use schemes and also using empirical corrections. But when we look at the calculations that we did, we are seeing that when comparing to the bare DFT calculations, which is the green here, we are seeing nearly 4 times or 5 times improvement in the mean absolute errors. And we know that the diffusion Monte Carlo, the fixed node version, is well suited for parallel programming, and it has a scaling of n to the cube, or it could be n to the power 4 as well. So this is a minor calculation that I did just to give an idea about what can be achievable, like using a scheme like this. So we can see that if we were to allocate the Titan for this study completely, that would mean that we will be able to get the formation enthalpy of a single material every nearly 32 seconds. So this is just to give an idea, and that would mean that we will be able to maybe simulate nearly 200,000 materials in the ICST database over 6 months. So that would be very useful for people who want to generate phase diagrams and to see from a material science perspective, to understand what should be the stability of the new compounds that they are interested in. So from here, I'll basically talk about the cobalt monoxide. Is that better? Okay. So here, what I want to mention that, so the first work may be considered as more like a benchmark idea that we wanted to benchmark different formation energies, but in the recent years, we are seeing that the efforts are in terms of simulating the simpler materials such as cobalt monoxide is towards more understanding the more ambitious compounds like lanthanum cobaltite that we wanted to simulate in here. So we can see that for lanthanum, I'll come to that again, but we are seeing that the lanthanum cobaltite, when it is grown and it's constant tightening the sample, we are seeing this kind of lattice modulation and this X direction in here so that the lanthanum separations are being modulated. And when people try to simulate this, not even this epitaxial case, but just the bulk lanthanum cobaltite, depending on the DFT functional that you use, you're basically getting different ground state magnetic structures. For example, with PV Sol plus U and U is equal to 4 in here, you're getting more like an antiferromagnetic ground state. But with an LDA plus U, you're getting more like a mixed spin or a low spin state as the ground state in here. So for this end, what we did was to first understand whether the code and the pseudopotentials that we use are accurate enough to simulate the cobalt monoxide itself. So basically, we know that there are 3 different polymers of cobalt monoxide, and which are rhombohedrally sorted rock salts, wurtzite, and zinc-lens structures. So when we simulated this 3 polymers using PV, scan, and scan plus U, we know from the experiments that the rock salt phase should be the most stable. And we are seeing that kind of qualitative behavior only when we try to use the scan plus U calculations in here. And that's not even exactly reproducing the difference between the zinc blend and wurtzite structures, which I'll come to that in a second. So here is the breakdown of all the energy differences between the 3 different compounds, and we are seeing that the green regions in here are the experimental energy differences between different compounds, and we are seeing that the red bar in here denotes the DMC, the calculations in here, and so far, in all the 3 different compounds that I've studied, we can see that the DMC is actually the only method that can reproduce the energy difference between the 3 polymers exactly. And we can see that none of the DFT functionals are here able to get even the qualitative energy difference between the zinc blend and wurtzite structures. So I also want to briefly mention similar work that has been performed in Oak Ridge National Lab that shares the similar ideas. That we have studied manganese oxides, vanadium dioxide, manganese nickelates, and 2, 3 2A3B oxides and like nickel oxide as well, which has been already studied a number of times. So with that, I want to come to more like a nanoscale understanding of the material. So what we are going to discuss here is the optical emission energies of transition metal doped insulators. And now we actually come to the area where we really need to use very large simulation cells. So we are basically working with the manganese +4 doping, and we would need to take into consideration dopant-dopant interactions to make sure that we are using simulation cells that are large enough. So the basic idea in here is, from the materials perspective, is to replace the europium plus doping in LED materials with a manganese +4 dopant, which is, we know that the manganese is much less sparse than the europium dope, and it will be of interest for for materials applications. And this is the type of the electronic excitation that goes through on the manganese atom, and we can see that the excitation is mainly localized on the manganese atom if you look at the EG and T2G levels. So we know that diffusion Monte Carlo is essentially a ground state method, but it is interesting to see how it would perform in a case like this where we simulate the excited state behaviors. And so far what we did was to choose 4 different host structures, which is aluminum oxide, manganese oxide, yttrium oxide, and potassium 2 silicon fluor 6. And so these host structures, they all have manganese doped insulators in them. And for some of the structures that are in here, especially for aluminum oxide, I needed to simulate up to nearly 80 atoms in order to make sure that I have the converged simulation cell. And what we see in here is that the red results are for the DMC results with the error bars, and the green squares are the experimental emission energies. And the rest of the results are for the DFT calculations, where the blue ones are LD plus U, and the cyan ones are PE, pink ones are PE plus U, and gray ones are HSE in here. So we are basically not really seeing too much improvements as we especially go from TDE to PE plus U. So this was really interesting as a demonstration of the failures of DFT. And I would also like to mention that this work was also featured in the JPCL. And just a brief note about this material, that when we started to simulate the excited state in this material, we need to make sure that the excitation is well localized within the simulation cell. And what we did in here was that this is the charge density from diffusion, fixed node diffusion Monte Carlo calculations. And we compared those charge densities from the LDA plus U charge densities that we used to prepare the trial wave function for these calculations. And we are seeing that we are seeing we're basically looking at the electron density of this electron, which flips to the P2G level of the minority spin channel. And we will see that actually the charge densities don't really differ too much when we look at the DFT versus DMC calculations, and these are extrapolated DMC charge densities. And it is important that the DMC is able to capture the missing correlation effects that would lead to accurate excitation energies in these compounds. So in addition to that, I also want to mention the recently submitted work that we performed for the magnetic properties of epitaxial and bulk lanthanum cobaltite. So this is going back to the cobalt monoxide discussion that I started early on in my presentation. So going a bit more detail in here, so what we see from the experiments is that we are trying to understand why lanthanum cobaltite, the epitaxial lanthanum cobaltite on strontium titanate, is paramagnetic. So when people grow these structures, they are seeing this type of lattice modulation. So if you look at the STM pictures in a closed manner, you can see that this feature is more prominent in these structures where you have basically one dark layer and two bright layers, and the brightnesses here are associated with lanthanum atoms. So there are two physical reasons that why this kind of ferromagnetism might be occurring in these systems. So one opinion would think that maybe in the darker layers we are seeing a larger lanthanum separations, and that will lead cobalt atoms to obtain larger magnetic moments, and which would drive the ferromagnetism in these structures. And the second effect would be maybe there are oxygen vacancy defects again within the dark layers, but the oxygen vacancies in this case would be able to drive the magnetization on the cobalt atoms so that the material would be ferromagnetic. So there are two different mechanisms that the ferromagnetism could be possible. Basically, in the first mechanisms, we are seeing that it is the rotation of the cobalt octahedra that drives the ferromagnetism, and the samples will still be stoichiometric. And the second mechanism is suggesting that the samples should be non-stoichiometric and there should be oxygen vacancies. But before going into that, there are still other debates. The lanthanum cobaltite is a very complicated material. So when we look at the bulk lanthanum cobaltite in here, we are basically seeing that again there are two different models which can explain its ground state magnetic structure. So the first model suggested, which is going back to even 60s, says that the ground state should be diamagnetic. And the second model, which is more recent one, this one is suggesting that basically the second model, I have to say that it relies more on the better sample preparation methods and single crystals. And we are seeing that the lanthanum cobaltite should be paramagnetic, anti-ferromagnet, about 100 K. But both of these works, none of them have observed long-range magnetism at lower temperatures. So that's why it's kind of puzzling that since there is no long-range magnetism is observed, the model 1 was relying more on the diamagnetic ground state, but the model 2 is suggesting that there are still local moments on the cobalt atoms, but they are not ordered. And the recent work again is suggesting that using the neutron diffraction spectra is that there are still nearly 4 to 5% cobalt-3 oxygen 4, or maybe some minor percentage of cobalt monoxide coexisting in the space. And we know that the cobalt-3 oxygen 4 is already a ferromagnet at these temperatures, so at lower temperatures near 0 Kelvin. So it is also known that this material would be preventing experimentalists to get a clean measurement of the magnetic properties of these samples near 0 Kelvin. So with this motivation, we were all set to calculate the lanthanum cobaltite using diffusion Monte Carlo. And what we did in here was to show that we basically looked at 5 different magnetic structures of the bulk structure in here, and we know that the cobalt is in the +3 charge state, so it should have 6 valence electrons. And based on that, we can have 3 different magnetic states on each cobalt atom: low spin, intermediate, and high spin structures. And depending on how these are oriented, so this is not a complete span of all the magnetic structures that can exist in the lanthanum cobaltite. But these were the ones that were studied in the literature most often. And we have seen that we basically need to use diffusion Monte Carlo to show that we need a method that can perform well, that maybe we can use a diffusion DFT method, which does good on the geometry optimization, but use diffusion Monte Carlo to understand which magnetic structure is going to be the ground state in here. So here is again the diffusion Monte Carlo calculations that we performed on these cells. And so in comparison to all the DFT calculations that we did, so basically it contradicts with the first model that I discussed from the experimental perspective, but it agrees better with the second more recent model that we are seeing basically like an antiferromagnetic ground state for the bulk lanthanum cobaltite. And the energy difference between the antiferromagnetic phase compared to others is larger when we did the PDSO plus U calculations. So going back to our main motivation in here is that we wanted to understand how this lattice modulation works in these materials. So we basically wanted to simulate how this structure is formed in the theoretical perspective. So we basically studied 3 different scenarios where we separated our simulation cell into 2 regions where the left side is the dark region and the right side is the bright region. And we optimized these geometries at the DFT level because these would be too much complicated. These cells would have 30 atoms in them. This will be too much complicated for diffusion Monte Carlo calculations. And what we found in the diffusion Monte Carlo in here is that this structure in here, the high-spin ferromagnetic structure in the dark layer and the high-spin antiferromagnetic structure in the bright layer, which resembles the bulk structure, can be formed in the with a little energetic with a little energetic driving force that we compare to bulk strain lanthanum cobaltite, which has the same strain on this X direction in here, so that we can see that the ferromagnetism can occur in a system with a little lattice modulation. But however, so far what we have found that the experimental lattice modulations that are observed are nearly 4.5 angstroms in here, but we are seeing 4 angstroms, which is the lanthanum distance in the dark layer, which is basically the size of the width of this blue rectangle in here. So we are doing further investigations on how the defects may change this structure. Maybe that could be other defects such as lanthanum anticites or cobalt anticites, which may change their locations as during this process and may give rise to this kind of much larger lattice modulations that are observed in the experiments. So the summary of this part is that we found that from fixed node diffusion Monte Carlo, an antiferromagnetic ground state is found for lanthanum cobaltite, and the MC explains the ferromagnetism on the axial strain lanthanum cobaltite, but it is not able to explain the large lateral modulations, which are nearly 4.5 angstrom in the experiments, and we are in the process of studying the defects on this thing. And again, in an effort to highlight some of the work that has been published, which is in similar nature to the work that I have done in this in the subject. So basically, in RML, we have already studied strontium ferrite or lanthanum ferrite defects and perovskite superlattices and zinc oxide defects using fixed node diffusion Monte Carlo. And for those who are in the material science field doing applications of these calculations can guess how large these simulation cells can go. And so based on that, I had a minor highlight of one of the features that have been recently implemented in diffusion Monte Carlo is the new hybrid representation that can be used within QMC type. So basically, the structure in here is we are dividing the real simulation cell into the blips. But what we can do is that we can divide the simulation cell into 3 regions, where the A region will be core, the C region will be intermediate, and the A region is the transition region between those two regions. So this is kind of similar to APW-like separation of the wave functions. And we are seeing that if you look at on the right in here, so the MF stands for the mesh factor. So mesh factor defines how large how dense your wave function should be. And we are basically seeing that with a suitable cutoff radius. So this work was performed on nickel oxide basically, and using a suitable cutoff radius in here, we can reduce the wave function density by half. So that would actually correspond to very large memory gains. So you can see that this is the memory gains by using this scheme is using the log scale is more than 10 times the reduction in the memory. So for some of the work that I presented early on about the lanthanum cobaltite, I was basically using this hybrid representation, which enabled me to go up to nearly 900 to 1,000 electron systems for finite size extrapolations. And there is also some improvement on the evaluation of the values within the core region for the values and the gradients of the wave function that we are basically calculating. So the summary in here that we want to show that the QMC benchmarks for perfect crystalline systems can be performed routinely in modest computers, and we are we are at a time where we are doing the benchmarking efforts mostly towards studying more ambitious systems compared to the DMC calculations, where in the past people would study DMC calculations with one or two materials at most, and that will make a paper. But now we are at a stage that we can simulate much larger systems, and the QMC pack has a very active support and the developer base, which enables even pushing larger simulations that can help for the material science applications. With that, I want to thank you, and I can take any questions that you have.